Hi, this is a short introduction to our work on a general method for calibrating stochastic radio channel models, that is, fitting the parameters of stochastic radio channel models to data using kernels. The state-of-the-art calibration method goes as follows. Let's say you start with a bunch of radio channel measurements, Y, and then you extract the multipath parameters, such as the delays and the gains, using some high resolution algorithms such as Music, Sage, or Esprit. And then depending upon whether your channel model is cluster-based, then you would fit a clustering algorithm to find its cluster parameters. And then once the multipath components have been clustered, then we fit the parameters of the channel model using maximum likelihood or least squares fitting. And in the end, we get a point estimate of the parameters theta of the channel model. The problem with such an approach is that at each step, we are required to implement a sophisticated algorithm such as the Music Sage or these clustering algorithms that themselves have a number of hyperparameters to tune. And the overall performance of the calibration method is unknown, although we might know the performance of each of these individual steps. Another problem is that such an approach is tied to the kind of model that you use. So if, let's say, you propose a different modification to a channel model, that means the calibration pipeline needs to be adjusted accordingly. And so there is no one method that you can use to fit different channel models. As a result, it's very difficult to compare different models on the same data set. What we propose is to use easy to compute general summary statistics of the data instead of going the multipath extraction and clustering route. So we compute these log temporal moments of the channel responses like this, and then use these to fit the model using our kernel-based approximate Bayesian computation approach, which is described in the paper. And in the end, what we get is not only a point estimate, but also a characterization of the posterior. So the uncertainty is also characterized in our approach as compared to the state-of-the-art method. So what we find is that we used this approach to fit the Saleh-Valenzuela model and the propagation graph model to 60 gigahertz MIMO channel measurements. And here the channel measurements are in black, and then the two models are in blue and red. And here is the power delay spectrum, the RMS delay spread, mean delay, and receive power, which have been plotted for the fitted models. And we see that our method is able to calibrate both these models to the data, and then without the need for any multipath extraction or clustering. And these models have very different mathematical structure, but they're still calibrated in the same way, which means that now we can compare the fit of these two models and make decisions based on which model is better suited for the data at hand. Thank you.